My name's Eric.
My name is Matt.
My name's Joe.
And my name is Aji, and we're going to take a look into the YouTube network. Next slide, please. So our goal for this project was to explore the interconnectedness of YouTube using a sample dataset from Stanford's SNAP database. Our three algorithms that we used were the BFS traversal algorithm, Prim's MST algorithm, and betweenness centrality algorithm. The BFS was used to iterate through all the vertices. Prims was used to find the distances of users relative to other users, and the betweenness centrality was used to find the user with the most paths through it out of all the paths considered, showing the most central user out of the entire sample data set, and kind of just showing who kind of who our sample surrounds. Next slide, please.
Yeah, so jumping into a little bit of the development of how we actually implemented some of these goals. The data set or the data structure we decided for our data was to use an adjacency list similar to the one pictured on the right. The reason we chose this was because the incident edges, to retrieve the incident edges from an adjacency list only takes degree V time. And this becomes very helpful for when we BFS or other algorithms of that nature. Additionally, we implemented a custom vertex, edge, and graph class with vertex containing a bunch of node IDs, edge containing the two vertices that are connected by the edge, and then our graph class itself containing two unordered maps, one vertex map that maps from a string ID to a vertex, and a other edge map that maps from a string to a list of edges. So that was the primary data structure that we sorted everything into. From there, we then went ahead and built off that data structure to implement our BFS traversal, our Prim's minimum spanning tree, and our betweenness centrality algorithm. Next slide. So for the traversal, the BFS itself, the runtime of this traversal is a big O of V plus E, where V is the number of vertices and E is the number of edges. Of course, BFS stands for breadth first search. And in our case here, we used a custom iterator that would iterate through a traversal of our vertex data types so that you could call operator plus plus and operator star to get the current vertex in the BFS path. Additionally, the adjacency list of vertex pointers was used so that when we dereferenced each of these vertices, we would actually get a correct reference to the correct vertice. Next slide, please.
Yeah, so the next traversal we did was Prim's minimum spanning tree. And this runtime is big O of n squared, where n is the number of vertices. And as you can see in this picture on the right here, so we used an adjacency list, and we also used an unsorted array in our implementation. And so this was big O of n squared. And that simplified a lot of calculations for us. So Prims, as a general overview, is a greedy algorithm that creates a minimum spanning tree based off a frontier from a starting vertex. So this is all based off weighted edges to find the shortest path. For our application, one caveat is that we created arbitrary edge weights since the YouTube data intrinsically doesn't contain edge weights. Next slide, please. So the next thing we did was betweenness centrality. And we used a really, really cool algorithm called Brand's algorithm that's kind of a modified breadth first search. And its runtime is big O of n times m, where m is the number of edges, n is the number of vertices. And this pseudocode you can see here is from the University of Konstanz in Germany. And so as you can see in this graph on the right, the big numbers represent the vertex IDs. The small numbers represent the actual betweenness centrality values. And as you can see here, vertices 2 and 3 have the highest betweenness centrality values and therefore are the most central. And you can kind of see that in this very simple graph. One thing to note here, though, is that Brand's algorithm is for undirected graphs. So these betweenness values you see here are actually doubled. So the real betweenness centrality values would be, for example, 2.5 for vertices 2 and 3. Everything would be cut in half since it's undirected and not a directed graph. Next slide.
So most of our critical issues revolved around the fact that the data we received were were anonymous and didn't really have real life analog. They were given as integers for the sake of anonymity of the users. So we were not able to have significant weights for different edges because there was no distance given or anything that could be used as a weight. So instead, we chose random weights incremented at a standard rate, and our conclusions were more general, just trying to figure out just how YouTube networks work, and you'll see that in the next slide. One of our issues regarding the code included our hash map, which did not allow for changes, and because it returned a const value or required a const value. And our solution was to use two maps to store the various values that we needed to access. Another issue that we had was that our iterator wrapped back around to the first node, and that was a pretty simple fix where we used the traversal list instead to iterate through our vertex IDs. Next slide, please.
So moving towards our conclusions, as Aji said, we did have some general conclusions about this information. Our primary goals being to use this data and our algorithms to understand YouTube specifically in more depth, and hopefully in a way that could actually be useful for a social network such as YouTube. We did find out that YouTube channels are incredibly interconnected. First, when we ran the Prim's MST algorithm for our entire data set, we learned that no matter which node you started at, it was really difficult to find a minimum spanning tree that had more than 12 or 13 nodes, with the maximum value we ever found being 14 as a maximum depth, the farthest you could get away from the starting node. And what that means is that the nodes themselves are so interconnected that there are so many different paths that you can take to get from one node to the next. It's very difficult to say that two nodes are not at all connected in this massive tree. And to that note, when we ran betweenness centrality, we found that the highest betweenness centrality rating of any node was on a particular node that was designated as node 4, which had a betweenness centrality rating in the tens of millions. And this was incredibly massive. This would represent, to compare this to what YouTube actually is, this would represent a very popular channel such as T-Series, Dude Perfect, or PewDiePie. And this actually served to us as being our application that we could use. We could use betweenness centrality as a rating for which channels are particularly popular. And then that might be what YouTube might show on its front page, channels that it would suggest to everybody, because we can already prove through the betweenness centrality rating that they have a ton of traffic going through them and they're incredibly interconnected. Anything else to add, guys? I think that concludes our presentation.
I think so.
I think so.
We
Thank
had a
you very
great time
much.
making it. Thank you for listening.
Thank you
Thank
very
you for
much.
watching.